Now see this example. So in using this example, we will see how to do subtraction, and also we learn how to do rounding and how to use God digits. I am assuming that, so our formats are in IEEE, okay, that means IEEE 754 format. You know the IEEE 754 format. But sir, it should be 32-bit, right? I am using only 12 bits. Yes, you are right. Why I am using only 12 bits? Because it is easy to explain, because you know, so if I take 32 bits, then I have to represent always 32 bits, and I have to manipulate the things using 32 bits, then unnecessarily dilute the main concept. If I take only 12 bits, it is easy to understand the things easy, right? So that's why I'm using only 12 bits, but the flavor is same. That means every rule we are using, which is, you know, generally a rule for IEEE 754 format. Only we are reducing the sizes of mantissa and exponent. Everything is same. Did you remember whenever we use 8-bit exponent in IEEE 754, then we used excess 127 format to represent positive and negative numbers. In the same way, when you have only 5 bits to represent, using the exponent to represent positive and negative numbers, we have to use excess. I will tell you the trick here. 127 is significance is 2 to the power of, see, out of 8 bits take 7 bits. 2 power 7 minus 1, 127. We have to subtract from 127. Since here only you have 5 bits, then take only 4. 2 power 4 minus 1, 15. So excess 15 is the right thing here. Okay, let us take excess 15. That is one thing. Let us begin doing a minus b. One is already positive, another is negative. Doing a minus b is nothing but again addition, correct? So let us do that. Now let me take a and b and let me do a minus b, okay? So first of all, let me focus on a. So what is a here? This is exponent, right? So this is mantissa. First of all, I write in 1.m format. 1 point. This one is mantissa. 1.011011, right? And sign is 0, means plus. 1.011011 base 2 into base power 2 power exponent. What is exponent? Exponent I represent using decimal. It is convenient for me. 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. This is 16, this is 1, 17. 17 minus, we know that x is 15 format, 17 minus 15. The b is, so 17 minus 15 is 2. B is minus 1 point m. M is 101010 base 2 into 2 to the power of this one, 15. Just check it out. Minus 15. 15 minus 15, 0. Right. So now you have two floating point numbers which are in IEEE 754 format. We have to do the subtraction, a minus b. So you know that, right? Whenever you have numbers, how to subtract, I will explain. Before that, first of all, we have to see the exponents. If exponents are not equal, then this is smaller number, right? We have to compare exponent, this one exponent, this exponent. Otherwise, directly you can compare here also. Now, did you remember one day, so I was teaching you XS 15 format, XS format, right? XS 127. Then at that time I asked you one question, why XS 127 format? If you represent positive and negative numbers in this some XSX format, then when this bit is 0, this bit is 1, then definitely I can say that this is bigger number, correct? So easily we can decide who is bigger, who is smaller. That means the comparator is easy to design. The old example, let's say you have some two unsigned numbers. How you compare them? Same comparator we can use here. Understand? That's why circuitry will become simple if you use XS format. So see the first bit 0, 1. This is bigger in that way. So now this is smaller. Whenever you have a smaller one, then we have to improve it. That means we have to increment by 2. Then only this exponent will become 2 square. So please refer my subtraction algorithm. I already explained you subtraction algorithm, right? Please refer that video if you don't know how to do subtraction. First step in subtraction is exponent should be equated. Second step is when you equate exponents, because you moved it to 2 units, then we have to shift the mantissa right side by 2 units. Let me do that. So I am shifting this mantissa by 2 units. Here I do first. So just shift it 0.2 0. Remember one thing, whenever you have 1.1 number, whenever I shift this to right side, it will be 0.11. In the same way here I am doing it. 0.011. See, this 1 was here, it came here. 11011010. Sir, we have only 1 2 3 4 5 6 7 significant digits, right sir? But you are using 1 2 3 4 5 6 7 8 9 significant digits. How come? So how can you have it? That's why God bits comes into the picture. That's why we use God digits. So these two are going to be stored in God digits. Okay, we'll see that. 1 0. So let me do right shift. Here I write it. 0.01101010. Sir, if it is 2 to the power of 0 and it is 2 to the power of 4, then you have to multiply with 4 times, right? That means you have to make it 2 power 4, then only exponents will become equal. Then we have to shift 4 times. When you shift 4 times, then you need 4 God digits, right? Then how you handle it? I use only 2 God digits, then the remaining 2 digits I ignore. Example, if you get 11 digits, you have only 2 God digits, then the remaining 2 digits are going to be wasted. That means we'll be discarding them. If you don't have any God digit, what you do? Example, you can represent a number with only 3 positions, let's say 1 2 3 like this. Suddenly you got a number like 1 2 3 4 5. What you do? If you don't have God digits, only I represent 1 2 3, maybe most significant digits, correct? That is what we are going to do here also. So here there is no such problem, correct? Now see 0.01101010. If you have any other digits, discard them, right? Now this one also, let me write in same format. 01, so I write clearly here 011011. So in these two God positions, we write zeros. Now after that, what to do? Subtract mantisas, because that is subtraction, right? Now let us do the subtraction. However, because already it is a negative number, b is a negative number, a is a positive number, subtraction is nothing but a minus b is nothing but addition of these two numbers, correct? Mantisas actually to be added, correct? Easily we can understand positive, negative. When we do subtraction, overall it will become a plus then this mantissa should be actually subtracted, but the value, one is positive, one is negative, then we have to we have to add them, correct? Let us do that. So 0 0 0 0 1 1 1 0, here I am doing it. 0 0 0 0 1 1 1 0 1 1 1 0 1 here, 1 plus 1 0 1 1 plus 1 plus 1 1 0, sorry, here you get 1 again, correct? Carry, and 1 plus 0 1. What I wanted to tell you is, if you have minus 0.25 and 0.5, if you subtract these two, if someone asked you to subtract, what is the answer? 0.5 plus 0.25, right? We have to add them, add the values, right? So that is what we did now. So let's cross check whether it is correct or not. 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 0, then carry will be 1, 1 plus 0 1, here 1 plus 1 0, then carry 1, 1 plus 1 plus 1 1, then you get here carry 1 1 here. Yes, perfect. So you got finally 1.110101110. These two are God digits again, remember. Now calculation is done. Once calculation is done, then rounding comes into the picture to avoid these God digits, because God digits are temporary. If you want to get rid of that God digits, we have to use rounding. So now try to get some information from this 1 0. Did you remember rounding technique? In the rounding technique, if the to be discarded digits are like 1 0 0 format, so 1 followed by all zeros, then what to do? We have to do tie break, correct? Using banking algorithm. What that banking algorithm says? Banking algorithm says check least significant digit in to be retained bits. These are all to be retained bits. In that, least significant bit is 1. Is it odd or even? Odd. Make it even. How to make it even? Add 1. So effectively we have to add 0.000001. If you add it, then 1 plus 1 0, 1, 1, 1 plus 1 is 0, here 1, 1, 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1. You get 1.110110. 1.110110. This is the final answer, which is mantissa. And what is the exponent? Exponent is nothing but 2 to the power of 2, I think, right? 2 square. So of course again we can represent it back in floating point model, right? This is what happens in IEEE 7054 floating point arithmetic. So finally you understood how addition subtraction takes place, and while doing that how these God digits can be used, and one more thing, rounding, right? So if you don't do rounding, if you don't use any significant digits like this, I mean God digits, then what is going to happen is directly we take, you know, only this part, then we add. Okay, so that is homework for you. Don't take God digits. If your number, example, what, let's say if you don't use God digits, what is going to happen, I will tell you. Initially you had like this, right? 1 point, this one, I'm talking about this one, 1 0 1 0 1 0, we had this one, into 2 to the power of 0. But you thought of making it 2 square. To make it 2 square, we have to do what? We have to right shift this mantissa by 2 positions. Then you get 0.01101010. Only your problem is now you have 1 2 3 4 5 6 7 8 9 digits, but you have only 7 digits. Then discard these significant digits, least significant digits. That is what you should do. That's it. Okay, everything is same.